Welcome to episode 9 of Crashcourse Cryptography. And today we finally reached elliptic curve cryptography. It's the cryptography that's being used in most blockchains, in most cryptocurrencies, and I predict actually in a lot of future internet applications. And you will see why. And elliptic curve cryptography has some very, very interesting applications. Now, if you're watching this completely out of the blue, I highly recommend you not to do this. Go back, watch some of the early episodes, because we are assuming you understand a lot of crypto already. So that's going to be very, very, very important. When we talk about this third group now of asymmetric or public cryptography. So we had RSA, we had Diffie-Hellman, and now we are coming to the elliptic curve. Now, elliptic curve is harder. Let's go into the writing pad here. So we're talking about here elliptic curve crypto, many times abbreviated as ECC, and that's what we're talking about today. Elliptic curve cryptography is harder than RSA and also the discrete logarithm problem, and that has a couple of advantages. And that's actually the advantage why it's being used also in blockchain, and that's data, because in RSA or also in the discrete logarithm problem, most of the keys actually have at least 1024 bits. And we talked about this because otherwise it gets too easy to crack them. In elliptic curve cryptography, because it is so difficult and it's actually so computational intensive, the minimum it takes is 160 bits. Most actually use 256 bits. That's also what's being used, for example, in Bitcoin. But that's obviously a lot less, right? And especially in blockchain where everyone needs to store all the data, it makes a huge difference if it's one bit more or less. It's doubling the size in this case, and in this case between 1024 and 256, massive, massive, massive difference. So how does this actually work? And what does this actually look like? When we talk about some of the general concepts, what you will see now is we're moving away from just numbers when we talk about RSA or Diffie-Hellman, and we're moving to geometric shapes. Some of the most basic geometric shapes we have here is, so let's call this a general overview. When we talk about some basic geometrical shapes, we obviously have spheres. The formula for a sphere is actually quite straightforward. X squared plus y squared equals the radius. Sorry, that's a circle, not a sphere. Sorry. Let's erase this here. Circle. Then we have an ellipse. In the ellipse, basically, it just gets stretched a bit. So we have a factor here, a times x squared plus b times y squared equals r squared. So it's the ellipse, right? So we have a circle. We have an ellipse. Obviously, my drawing, don't focus too much on the drawing. I'm not that much of a drawer. And now we get to something called an elliptic curve. An elliptic curve has a similar formula here. So we have a y squared equals x cubed plus ax plus b. There are some factors that are relevant to this. For example, a, b need to be elements of the group. And there's an additional formula or an additional condition that for a cube plus 27b squared is not allowed to be 0 mod p. So we have this mod p function as always. So the expression mark and equal is not allowed to be, or is not equal to 0. This is just a small kind of side note there. And here is where the shape looks like. Now the shape looks very, very, very different to anything that you probably are used to. So let's kind of draw this a bit narrower here. So let's draw up this very basic elliptic curve. So if we have this plane here, then let's make this a bit fatter again. And let's draw this in blue. Then this is what most elliptic curves look like. Again, not to scale, not accurate. This should be round here on the left, but you're getting where I'm coming from. So this is what the shape kind of looks like. You can go on Google, look up images, way better drawers than I am. That's all fine. One thing that you see already is that this thing is symmetric. It should be, not when I draw it, obviously. So it's symmetric, and you can see this obviously here from the y square. So it makes this symmetric. Let's look at some of the factors. Let's look, and this is now it gets very, very important. These elliptic curves are standardized. So don't come up with your own elliptic curves. They get all standardized, they get checked, because this is what's very, very important. We need what we call a cyclic group. So remember, we need to generate a point. And we need to be able to generate this entire curve, not by me drawing it this way, but basically we need to be able to generate it in a random order. So one point comes here, then this point comes, then this, then this, then this, then this, and then over time, the entire curve gets generated in a random order from the generator point in an unpredictable order. So it's always the same order, but it's unpredictable which point comes first, right? This is the power here of cryptography in this case. So we need this generator point, and from this generator point, the entire curve has to be able to be generated. There is actually, it's quite difficult to actually calculate all the exact points. But so what you're trying to do is, you're trying to have, as always, you're trying to have the number of points, the order, basically has to be the p, the prime number, that's the modulus, right? The modulus p. So, and you can calculate this. There's actually Scoof's algorithm that we're not going to go into, but I'm going to write it up for you that want to look at how this works, which bases a lot on the Hess's theorem. And there you basically calculate how many points actually get generated out of a group. And is it a cyclic group? Do you have a generator point? Can you generate the entire group out of it? And you need to find this generator point, and you need to have standardized curves. And this is very, very important to understand, because you don't want to come up with these things yourself. For example, if we look at the Bitcoin curve, then we have a equals 0. We have b equals 7. So if we fill this in here, then we have y squared equals x cubed. This is 0 plus 7. So this is the Bitcoin curve. So let's look at the Bitcoin curve. This is y squared equals x cubed plus 7. And then we have this generator point that's pretty much in infinity, huge coordinates, right? So we have an x coordinate, a y coordinate, and now it gets very, very interesting, right? Because that's now the tricky part. Whenever we are discussing these things right now, we don't get numbers. We always get an x coordinate and a y coordinate. So this is where we need to understand the basic principles. Looking at the cyclic group, obviously we need to have all the functions, all the capabilities. So every element needs to be part of the group. And another thing is we need to have the inverse. The inverse is, for example, the additive inverse is very simple. We always have a symmetric point, and these symmetric point. So let's say this is, in this case, let's say this is minus r, then this is positive r, right? So they are symmetric. They get flipped over. And obviously, another thing we need to have a group operation, right? So we have an inverse, and we need to have a group operation. And the group operation is addition, but this works a bit different to what you might be using as normal addition. And how this works in this case is, we have this generator point, and then we add to a point another point. So let's say in this case we have here, and we start, let's say, and we're going to use it very simple now. So let's say this is point P, and let's say here I have point Q, and let's just say it's that lucky that I have a line here that goes, if I add P plus Q minus r equals 0. So in this case, if I flip it over, then p plus q equals a new point called r. So how do I get to this new point r? Very simple. I have point p, I have point q, I get to the negative r, and then in order to get to the positive one, I need to flip it over and I have a new point r, and now I would be doing the same thing. So I would now draw a new line and I would get a new point, and so on, and I keep going. One thing that's very interesting about these elliptic curves, and that's the property they have, whenever I have 2 points, then and I draw a line through, I get a third point. So always can add another point, and that's very, very important. Obviously, there's an exception to this, and the exception is if it would be a complete vertical line. And this is why we have some conditions, so this can never happen. Right? So this is where it gets now very interesting. Now, let's think a couple of things through. What would happen if I would then say, let's add a generator point constantly to itself, right? So basically do p plus p. So basically have 2p. How would this work? Well, what we're basically doing is, in this case here, let's use a new p just so we can draw it a bit easier. Let's say we have a new p here, and we would add this point, so we get closer, 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 closer. What we actually get is we get the tangent. And so we would have a tangent, and that hits another point here, and this is now the new point here, and let's say this is this new point, in this case minus r, and then we would have to flip it up here, and we get the positive r here. So this is what the tangent then becomes. So if I actually add a point to itself, it becomes a tangent. Now, the interesting question is, how can I calculate on these things, right? How can I calculate this through? And so let's go down now, and actually what we're trying to calculate here is the slope. And the slope is very simple. It's basically, if I have the slope s, it consists of y coordinates and x coordinates. Now, the y coordinate, the x coordinates, remember, is this one. So this one is x, this one is y. So the shorter x is between the points, the steeper the slope, right? So I have to put this on the bottom. So I have x2, or we can call it, in this case, what happened here now? So in this case, it's xq. So of the second point, minus xp. So xq minus xp on the bottom, and on the top I have the y coordinate. And on the y coordinate, I want to have a really large number, because here, the smaller, the bigger the slope. So I want these things close together. And here, yq minus yp, because the bigger the slope. So now what we could do, and I'm not doing this, but what I could do is I could start, why do I have this line in there now? Okay, I need to get rid of this line somehow, but it doesn't matter. So what we could do is we could calculate all this through. This is not that relevant. The only thing we need to understand, right? You can go on YouTube and you can see slope calculations. This is very, very basic geometric math that we could spend half an hour right now and do the entire calculation, going from one point to the next to the next. What you need to understand is the following, and we are going to get to the exact same thing now that we have done in Diffie-Hellman. And it's, in this case, we call it scalar multiplication. And it's basically the square multiply algo. And this is going to be very, very important, because what we can do now, it's very, very straightforward. I know p, I can calculate 2p. Then I could do 2 times 2p, so I have the 4p, I have the 8p, I have the 16p, and so on and so on. So with just a couple of calculations, I can get to any point on this curve, because I don't need to calculate every single point. I can just calculate basically directly where I want to go. As long, remember, it's the same thing as spending money, as long as I know the exact amount that I have to go. And now this is where we're starting now already. Basically, we have this private key. Okay, we have the private key. And the private key is how often I add the generator point to itself. Exactly the same thing as in the discrete logarithm problem. Just now we are talking about points on a curve. And because, and this is important, right? The group repeats. I have the exact same concept as in Diffie-Hellman. This is really important. If I have a private key, then my public key is the coordinate where I get to. Right? That's my public key, the coordinate. The private key that stays private, so that's why I mark it red. The private key is how often I add the generator point to itself. And in theory, I would need to do this 2 to the power of 256 times if I want to test everyone. But because I know exactly how often I do it, I just have to calculate here until I get to 2 to the power of 256. So I can get here to 256. It's quite straightforward. It's quite easy. It takes me, and you can calculate this, around 120 calculations max. It doesn't take much more. Versus doing, I don't know, an insane amount here. The public key, the coordinate, can be public, just like on Diffie-Hellman, where we have basically this concept of the clock. And now this brings us to one concept. Wait, I forgot something. I forgot to mention something. Now, obviously, all this is happening in mod P. So we have this large prime number. The reason we're not doing this in mod P, but we're doing this just regular, is because in mod P, this stuff looks really weird. You can look up like pictures on how elliptic curves look in mod P, and you're gonna sit there and you're like, this is not even recognizable as a curve. But the same ideas and the same concepts still apply, because it always works the same thing. We have this curve, we just put it on mod P so it looks completely different, but the same principles apply. We have a generator point, and we add this generator point to itself constantly. And the way we do it is by calculating the slope. And by calculating the slope, we can add it, and then we have the scalar multiplication, in this case, the square multiply. So depending on, that's my private key. This is important. I choose this as with a random number generator. I generate this private key. Don't generate this with your head or by yourself. Do this with a random number generator. And then I add it to itself, and then I get the public key, which is the coordinate, and I can give this publicly out, right? So this is always the same concept on this entire tool. So now we get to a very easy part here, and that's encryption decryption. And you should understand this already. Encryption decryption simply works like the Diffie-Hellman key exchange. The same thing. Because if I have a private key, so let's have Alice, and let's have the private key Alice, generates the public key, Alice, and then I have the private key Bob, generates the public key Bob. And so now they can exchange the public keys, so they exchange those, and add their own private keys to each other, right? Always add own private key. But because no one knows the private key, an attacker from the outside cannot understand this. If this confuses you, go back to Diffie-Hellman, and then you have a shared secret. They can be used as a session key. And that's how simple, basically, elliptic curve works. The only difference is it's so much harder to attack because the calculations are a bit more intensive. So it just takes a little bit more time, and that's why it is way more efficient, especially from data storage here. That's why you only need 256 bits in this entire concept there. If you wanted to crack this, right? So let's say you want to crack this. Let's go and talk about crypt analysis. If you want to crack this, what you would have to do is called a square root attack. And in this case, if we had a key to the 2 to the power of 160, then it would take you 280 attempts. And this is still hard. This is not that easy to be solved. However, and we're going to be talking about this there's no known more efficient way to crack this other than just really going through this with this so-called square root attack. But with Shor's algo, which especially with quantum computers, this could be vulnerable. And obviously this is a humongous discussion in cryptocurrencies, because that is going to be the reason why in crypto we need to upgrade them. We definitely have to upgrade them at some point when quantum computers become more and more powerful. There is one last thing though, and the reason this is so simple now for you, and for a newbie this is completely out of this world, is because you have all the background. Elliptic curves are insanely complicated because they are so abstract with this curve, and adding the curve to, like adding a point to itself. What is a generator point? What is a cyclic group? All this stuff is very, very complex, having a group operation. But if you understand all this from the other algos, it gets very, very simple. And you understand all these things. You understand how to calculate the slope, you understand the scalar multiplication, and then you just understand, okay, I have a public key, the other person adds his or her private key, and I can do it to his or her public key, and we all get to the shared secret, similar like Diffie-Hellman does. There is one key thing, and that's what's called a nums. And that's a number up my sleeve. It's basically this concept of playing cards and having an ace up my sleeve. And this is a huge discussion, and this is a humongous discussion, especially because all these curves, these standardized curves, have been proposed by the NSA. And so obviously, interesting thing. Where do all these points or these numbers come from? Have they been enough tested? Because there are some classes of elliptic curves that are particularly weak, and with special purpose algorithms, they could be cracked quite easily. And we've seen this before, so this is not something new. And so if you have this number up my sleeve, this basically means that NSA has found some weird curves that look secure and look great, and just tried and tried and tried, but actually they could actually crack this, and they could fight this. There's no proof to this. This is purely mathematically possible. I mean, this exists, and actually it has been shown. MD5 had this problem, something we're going to be discussing when we talk about hashing algorithm. We had this problem. Blowfish had this problem. There's a lot of examples where we had nums, and so obviously, where do the random seeds for example, the Bitcoin curve come from? The answer is, sadly, we don't know. There is no justification to the numbers, especially, for example, in Bitcoin. Why did this curve get used? Why not a different one? And these are major, major questions. Satoshi Nakamoto never clarified clearly on why he chose one curve over another. And so this is a huge, huge, huge question that a lot of cryptographers have always kind of highlighted and always pointed out with elliptic curve cryptography, that there could be a nums. And this would be obviously very, very critical. Now, obviously, since at some point we need to upgrade the cryptography behind Bitcoin anyways, this is probably going to be passé, but it's still a very, very, very relevant and interesting question. Let me know what you think about all this. Let me know if everything makes clear. We have done all the three major public key algos now. We've done the RSA, Diffie-Hellman, and elliptic curve. Elliptic curves, quite abstract, but because you have all these bases, I can really compact that now, and we can pump through this in quite a rapid speed, and I hope it makes it clear. Because this is going to be relevant when in the next episode we're going to talk about signing, because so far we've mostly talked about encryption and decryption, but let's talk about signing, basically using the private key first. And we're going to discuss this with all three algorithms. Then we're going to finish the general cryptography with hashing algorithms. And then the course is going to shift over and go very, very specific to crypto and blockchain. We're going to be discussing a lot of specific things. And so I hope you have all the foundation here. Let me know what you think. Give me a thumbs up. Let me know some positivity in the comments. If you have a question, let me know. And if you don't want to miss anything, subscribe to the channel. I'll see you at the next video. Yours truly, Julian.